kind of weird, like, okay, last classes were a week ago, but it feels like I've been in a classroom forever. Okay. So, today we are finishing up chapter 3 on solving A equals B by direct methods. And the next time we'll look at iterative methods for the same kind of problem, which I personally find more interesting. But there's a very important concept that comes up in this section, that is the notion of norms, a vector or matrix. If you're familiar with norms, at least in a limited sense, like in calculus, learn about the magnitude of a vector, the square root of some squares of a component, sort of the distance between the point and the origin. Now we need a similar notion for magnitude of a matrix. That's something I'll be covering soon. Okay, so on this Valentine's Day numerical analysis class. Okay. Now, so we've seen various algorithms for solving A equals B, and we describe those algorithms in Gauss elimination or Schlutsky decomposition or whatever it is, and we have an answer. But as we've seen, this was covered last semester, we're performing floating point arithmetic. Floating point arithmetic introduces error into just about every computation, and that error is going to accumulate over many computations. So it's been an issue already in terms of pivoting schemes. We choose pivoting not just to avoid dividing by 0, but also to minimize the spread of round-off error. And for H equals B, that can be a serious problem if not careful. Okay, so since we're trying to quantify error in the computed solution to H equals B, we need a notion of magnitude of a vector. And since we're dealing with matrices, having a notion of magnitude of a matrix is also going to be important. So, I'll start with getting into norms. So this is a notion of magnitude that we all will be familiar with. For a real value vector would be the square root of some squares, or if x was complex, we'd be taking the absolute value of each element and squaring that. In the calculus books, this is one I've been using lately, we use a single bar to indicate magnitude of a vector, kind of like absolute value, which I'm not really a fan of. We're going to use a double bar to indicate magnitude or norm of a vector or matrix. Now, it's a concept that's quite consistent with absolute value, but just to make clear that it's not just absolute value. So, if we're going to have some notion of magnitude of a vector, not limited to this one here, what should such a measure of magnitude have? What properties should it have? So for one thing, certainly magnitude should never be negative. It should be a non-negative real number. And the only time that the magnitude of a vector should be 0 is if the vector itself is a 0 vector. So that's an important property that if you have some notion of magnitude, if you think about work as a notion of magnitude, if it's going to fail, it's usually going to fail because of this. Also, if you scale the vector by some factor, that should scale the magnitude by the absolute value of that scaling factor. So if I take a vector x and I look at say minus 2x, the magnitude of that should be twice the magnitude of the original. It only makes sense. And then we have triangle inequality needs to be satisfied. Okay. So any function on a vector space that satisfies all three of these conditions qualifies to be a norm. Now, the norms that we'll be interested in are called the P norms. So it's a generalization of a Euclidean length that you've seen before, where we take all the elements of the vector, we raise their absolute values to the p power, whatever p is, add them up, and then we take a result to the 1 over p power. Now, so you're already familiar with this in the case of p equal to 2, but here's some other ones of interest. Okay, so we have the 1 norm. That's just some of the absolute values of all the elements. The 2 norm, that's the one we all know, the Euclidean length. But it's worth noting that the 2 norm of a vector can also be written this way, as the square root of the dot product of the vector with itself. But I want to point out here, because I don't think that this has come up before in this class. I have x with a superscript h, and that is called the Hermitian transpose. Because you've seen superscript capital T refer to transpose, but this is not exactly the same. So the Hermitian transpose is defined to be, you tell me how it relates to a regular transpose.
Complex conjugation.
Yes. So if you take just plain old transpose and then take a complex conjugate of that, then that's a Hermitian transpose. Now, if a vector is real, it doesn't matter, because conjugates wouldn't affect anything. But I use Hermitian transpose because if the vector is complex, and it seems for real numbers, it's redundant to take the absolute value and square it, but not if it's complex. In order to satisfy this property, that the norm of a complex vector is always a non-negative real number, using a Hermitian transpose is necessary. And that is equivalent to what we see here, taking this sum of squares of the absolute values of whatever complex numbers we have. Most of the time, when you have something that works out for real vectors and matrices, and you want to generalize it to complex vectors and matrices, that generally involves taking any transposes and replacing them with Hermitian transposes to make things work out the way they should. Okay, we don't really deal with complex too much in this class. And now, if you take the limit as p goes to infinity of this expression here, what ends up happening is when you raise the elements of x to higher and higher powers, that ends up emphasizing the largest element more and more. So in a limit, the infinity norm of a vector is just the absolute value of the largest element. Every time I think about the infinity norm, I remember the very first programming course I took when I was a freshman in undergrad. And the language involved was Pascal. So I had to write on the final exam Pascal code for computing the infinity norm of a vector. And that meant just taking the largest element. And I got it wrong because I forgot to account for the possibility of negative elements. I'm so embarrassed. That's stuck with me. Okay. Now, for most part, what we see, the trend that we see is that as the kind of norm increases, the p part increases. Like if we have p greater than q, then the p norm is less than or equal to the q norm. So if I were to take a vector x, same vector x, take like a 1 norm, 2 norm, 3 norm, 4 norm, all the way up to infinity, I would see the values of those norms generally decreasing, or at least not increasing. And the reason why is, like any one of these norms is greater than or equal to the size of its largest element. The infinity norm includes only that, but the other norms for finite p have some baggage, if you will, from the other elements. Now, one very important concept when it comes to different norms and how they relate to one another is the notion of norm equivalence. So all P norms satisfy relationships such as this, that for all x, the P norm of x is less than or equal to some fixed constant C2 times the Q norm of x, and it's bounded below by some other constant C1 times the Q norm of x. So this applies for all x. And for two given norms, you can try to figure out what those constants C1 and C2 would be. They tend to relate to the dimension of the vector, the number of elements it has. Now, the reason why this is important is for convergence of a sequence of vectors. So suppose you have a way you could define a sequence of vectors converging. Okay, I can have a definition right here. That vectors xk, the sequence, converges to a limit x if this is true, that if the norm of difference between xk and the limit x goes to 0 in some norm. Now, I don't have to specify what norm it is because they're all equivalent. So if I know that a sequence of vectors converges, and let's say I prove it converges, and let's say the one norm, then I know automatically it's going to converge to the same limit in all the other P norms. Any norm that the one norm is equivalent to. So you don't have to worry about having a situation where by measuring in one, say the one norm, this sequence of vectors converges to some limit, and then you check converges to the two norm, and it converges to a different limit, or maybe it doesn't converge at all. It's not going to happen. Like the rate at which it converges may be different, but the limit is the same regardless of the norm. Also, if this is true, then that would imply that each individual component of xk converges to the corresponding component of x. And the reason why we know that's true is because of this property of norms right here. The norm of the vector is 0 if and only if the vector itself is 0. In other words, all the individual components are 0. So convergence of a sequence of vectors to a limit vector is equivalent to all of the individual components converging, as you would expect. Okay. Questions so far about vector norms or convergence of sequence of vectors? The last part is going to become particularly important when we look at iterative methods. Because if you're generating a sequence of vectors, x1, x2, x3, that you hope converges to the limit x, which is the solution of ax equals b, you want to know that the error in those iterates really is going to 0. Okay. Now, for two norms specifically, we have this helpful inequality that you may have seen in calculus, the Cauchy-Schwarz inequality. And what that says is that the absolute value of the dot product or inner product of two vectors, x and y, is less than or equal to a product of their two norms. Okay. Now, in fact, in general, the dot product is equal to this times the cosine of the angle between them. But since cosine can be at most 1, we have this inequality here. I'm going to, in the case of the vectors being real, I'm actually going to take a little moment to prove this Cauchy-Schwarz inequality. Okay. So let's assume that c is some constant, and I'm looking at the 2 norm of a vector x minus cy. Now, the 2 norm of any vector has to be non-negative, so I'm starting with this point. But then I can write out what this is. Now, the 2 norm, as I mentioned earlier, 2 norm of a vector is a square root of dot product with itself. So here I have the 2 norm squared, so that's equal to the dot product with itself. But then I expand it out, and using the properties of the dot product, I get this. So basically, I'm foiling this. Now here I have the dot product of the vector itself, which is the 2 norm squared. I have that over here too. So that goes down here. Now, if we're assuming everything is real, for real vectors only, the dot product is commutative. So I'm allowed to combine these 2 terms here. But otherwise, if they were complex, I'd actually have 2 times the real part of this. And I know I've done a complex version of this before, but if I try to think about it now, I'm just going to embarrass myself. I'm not going to. But of course, I want to do it later. Works out sometime. But it's kind of a pain. Now, what you have here, if we think of this expression here as a function of c, the constant c, it's a quadratic function. So here we have ax squared plus bx plus c, where this right here is a. We have 2 dot product of x, y, or minus 2 x dot y is the b coefficient, and then this is a constant term. So if we apply the quadratic formula to this quadratic, then this is what we get. But the quadratic has to be greater than or equal to 0. So anytime you have a quadratic that does not touch the, it does not cross the x-axis, then the only possibilities are that you have a double root, or you have no real roots at all, that you have complex roots. So this discriminant is not allowed to be positive. If it was positive, we would have 2 distinct real roots, and then this inequality would be violated. So you take this expression under the square root, you say that it has to be less than or equal to 0, and then you just simplify, and the Cauchy-Schwarz inequality pops right out. Doesn't do it. Questions on how this played out? All right, so that's vector norms. Now we need to have a notion of a vector of the magnitude of a matrix. And it's not as straightforward as like if you take the matrix and now you rearrange it into a vector and take the norm of vector. It doesn't work that way. We have what's called an induced or natural matrix norm that's defined in terms of a vector norm. So if I have some vector norm, like one of the p norms, the norms in this fraction here, those are vector norms. But so I'm defining the matrix norm of A to be equal to the, sorry for real analysis reference, the supremum taking over all non-zero x of norm of ax times norm of x. So the maximum ratio that you can get of the norm of ax to the norm of x. Now, another way of writing it is you can take a maximum over a set of all vectors of unit length. So norm of x is equal to 1 of just a times x. Now, the reason why I can say max in this case is the set of all vectors with magnitude 1 is a compact set. And as we know from real analysis, the continuous function on a compact set has a minimum and a maximum. Okay, but here the set of all non-zero vectors, that is not a compact set. So I have to settle for the supremum or least upper bound. I can't be sure about the maximum is actually in the set. Okay. Now, here are some matrix norms corresponding to the vector norms you see. So the one norm, since the matrix is induced by the vector one norm, is defined to be, you take the sum of the absolute values of all entries in a given column. All right, so then you can find each column sum. It's the maximum of those column sums. I have here so I have in the appendix, second appendix is all linear algebra background with one. Well, all the information on norms. Yeah, so here I have on this page, this is the proof of the formula for the one norm of a matrix. So what I need to do is I need to look at the one norm of A times X, where X is any unit vector. So because X has a one norm that's equal to one, it means that the sum of all the absolute values of the entries of X has to be equal to one. So what I can do is I can break down what is the one norm of A times X. Well, that's the sum of all the absolute values of all the components of A times X. But then I can express the elements of A times X using this formula, it's a little bigger, for matrix vector multiplication is being used here. But then, it seems like anytime you're trying to prove something at the end of an expression that has more than one summation, the key to a proof is to rearrange the order of the summations. That always seems to play out that way. Sorry, we have AI doing proofs by now. Maybe we are. So, if I use a truncal inequality, then this equals becomes less than or equal to. And now I can have the sum over J of all the absolute values of the elements of X. And then I have this expression, the sum over I, going from 1 to m, this expression in the large parentheses is the sum of the absolute values of all the entries of A in a column of A. So this right here is the column sum for column J. So then I can certainly bound the J column sum by whatever the maximum column sum is. But this expression right here, because I'm taking the maximum over all J, is now independent of this J right here. So I can take this expression of this maximum and pull it out of the summation. And I'm left with the sum of all the absolute values of the elements of X, which is 1. So that's why this part can just go away. So now I've established that the one norm of AX is less than or equal to the maximum column sum, whenever X is a unit vector in its norm. Now, right now, all I've shown is that I have its upper bound. I do not know if it's the least upper bound. So what I have to do to complete the proof is if I can find a specific X so that this inequality becomes equality, then I've established the formula for the norm. And the way I can do that is I can set X equal to a particular column of identity. Because whatever column has the maximum sum, I'm going to call that column capital J. If I set X equal to E sub capital J, then the one norm of A times X will equal this, not just be less than or equal to it. And that completes the proof. questions about the proof? Okay, that's the one norm. The infinity norm is similar. So the infinity norm of a matrix is equal to the maximum row sum. So you take the sum of the absolute values of all the entries in a particular row, whichever one of those row sums is the largest, that's the infinity norm. And the way you would prove that is similar to what I just showed you with one norm. You're again using the formula for a matrix vector product. You just have to choose a different x to show equality of the upper bound. So those two norms are fairly straightforward to compute. I can't say the same about the two norm of a matrix. So a two norm of a vector is easy enough. That's just the square root of some squares. We don't have any such simple formula for the two norm of A. So the formulas I can give you is it is the square root of the largest eigenvalue of A to reach transpose A, which is guaranteed to be a real number. Actually, it guaranteed to be non-negative real number. Another expression for the two norm of A is the largest singular value of A. I don't really talk about the singular value composition in this class, even though my advisor invented the algorithm for it. But it's covered in the more graduate version, 610. Now, the difficulty with the two norm is it's very expensive to compute. So in a general case, like computing the singular value composition where the eigenvalues takes order n cubed floating point operations. Now, since you don't want all the eigenvalues or singular values, you just want one in particular, but that could still be pretty expensive. Maybe it's possible to do it in n squared flops, but it's not easy. In MATLAB, there's a function norm that you can use to compute whatever norm you like of a vector or matrix. The default is to take the two norm, even though for matrices that can be pretty expensive. So if you're trying to take a norm of a matrix and you're concerned about efficiency, you might want to choose a different one. Okay, there's one other matrix norm of interest. It's called the Frobenius norm. Now, Frobenius norm is actually pretty straightforward to compute. It's like a one norm infinity norm. It's like if you took the matrix A and you flattened it into a vector and then took the two norm of a vector. So you're taking the sum of squares of the absolute values of all the entries of A, adding all of them up, and then take a square root. Now, the Frobenius norm is it's not induced by any vector norm. There isn't any relationship like that. But it is used in quite a few applications, and it's a lot easier to work within the two norm. You may be wondering, like, well, since the two norm, out of all these four matrix norms, is by far the most difficult to compute. So why bother with it? One reason is it's differentiable. So norms in general are continuous functions of the elements of whatever you're taking a norm of. But the two norm for vector matrix has the advantage of also being differentiable. And that makes it very useful for optimization problems if we're trying to minimize something. Okay. All right. So questions about norms before I actually start using them. Not over. Got it. Lunchtime almost. Okay. All right, so I'm going to use norms to define the condition number. Now, the condition number, for those of you who were in the corresponding class last semester, is a very general concept so this was covered like in chapter 2. The notion of backward error analysis. That if we have some problem such as ax equals b, we're not limiting ourselves to that. Then we have forward error, which is just the difference between x and the exact x and the computed x. Now, in backward error analysis, we assume that the computed solution to whatever our problem is happens to be the exact solution of what's called a nearby problem. So here, the matrix A is perturbed a little bit by some matrix epsilon times capital E. So because the problem has changed, naturally the solution has changed. And we have called solution x of epsilon, because if epsilon is equal to 0, then we're back to solving ax equals b. So x of 0 is the exact solution. Now, so back when I covered error analysis in general, having adopted this notion of backward error analysis, that led to what's called a condition number. This perturbation, this epsilon e that we're adding on, that amounts to the backward error. So the forward error is the error in x. Backward error is how much the problem has to be changed for the solution to become our computed solution. And the condition number is a ratio of the magnitude of the forward error to the magnitude of the backward error. Okay. So we want to try to use norms, properties of norms, to bound this. This is the error in our computed solution. But what we're actually going to do is we're actually going to look at relative error. All right, so relative error is the difference between computed solution and exact solution divided by the norm of the exact solution. So relative error is right here. Now, what I can do is I can rearrange this equation I want to be able to solve for x of epsilon, but in a way that uses A inverse, because I can certainly multiply both sides of this equation by A plus epsilon E inverse and get a formula for x epsilon that way, but that doesn't help me. I really want an expression for x epsilon in terms of A inverse. So what I do is I take this term, the plus epsilon E, move it to the other side, and multiply by A inverse. It's not an explicit formula, but it's one I can work with. So x of epsilon here is replaced by this. Now, A inverse times B is x, because that's the exact solution to our original problem. So this term, A inverse B, cancels with this x. So now I'm left with this. Okay, but now I have the norm of this complicated expression up here, divided by the norm of x. Everything here is a vector norm. But now I can take advantage of a very important property that I haven't yet mentioned of matrix norms. And it's called the submultiplicative property. And that says that the norm of a product of matrices is less than or equal to the product of the norms of the individual matrices. Now, generally, a matrix norm is defined to have the same properties as a vector norm. That must be non-negative, scaling the matrix scales the norm, must have a triangle equality. There are some books that will include the submultiplicative property as part of the definition, but and others that don't. But what I can say is, even if you don't include it in the definition, generally matrix norms that we deal with, like all the P norms, the Frobenius norms, do satisfy this property. In fact, you were going to ask me, is there a matrix norm that doesn't satisfy the submultiplicative property? I'd be like, I have not heard of it, but I guess it could exist. But why would anyone want to use it? So if I make use of this property up here, then that lets me pull pull out the norm. I don't care about the minus because norm is effectively taking the absolute value anyway. We have pull out the norm of A inverse, also the norm of the matrix capital E, the epsilon. I pull out that down here, and then what I do is, so using some multiplicative property accounts for everything you see here, except what I've also done is multiplied and divided by the norm of A. So then what I do is I have the norm of A times the norm of A inverse, and I'm going to call that kappa of A, which is the condition number of A. So now what do I have? That the relative error is bounded by the magnitude of perturbation of the problem, the condition number of A, and then I have this. This is the relative change in the problem, because I start with matrix A, I perturb it by epsilon E. So the epsilon and this fraction here represent how much the problem has changed in a relative sense. And then I have norm of x of epsilon over the norm of x. This factor is not particularly interesting because as epsilon goes to 0, this converges to x. So for epsilon small, this fraction is going to be roughly 1. So what this inequality is really saying is the relative error in the solution is bounded roughly by the relative change in the problem times the condition number, which is consistent with how condition number is defined for general error analysis concepts in chapter 2. This right here is for relative forward error. The epsilon times this fraction right here, that's for relative backward error. The condition number is the ratio between them. So a condition number is a measurement of how sensitive the problem is to, or how sensitive the exact solution is to changes in the underlying problem. So if you have Ax equals B, and you make a small change to A or a small change to B, how much is that going to change the solution? So error or perturbation in a problem can be amplified by as much as the condition number, the error of a solution. So what that means is if the condition number, kappa of A, is large, that's a big problem, because that means a tiny change in the problem could result in a large change in the solution. And we say in that case that A is ill-conditioned. Now, that is, the condition number, keep in mind, is a property of the problem, not the method used to solve it. And the reason why that's terrible is because if you have an ill-conditioned problem, any method you could throw at it is going to have difficulties. So if you want to, basically you need to try to see if you can reformulate the problem somehow to get around it, or find out a way to put up with the ill conditioning. But it's going to lead to additional computational expense anyway to deal with it. Another way to interpret a condition number is if a matrix is ill-conditioned, it is in some sense close to being a singular matrix. In other words, the matrix is almost not invertible in the first place. Because if the matrix is becoming more and more singular, what would happen is the condition number is approaching infinity. And as I mentioned previously, it's better to use the condition number than the determinant to get a measure of how close the matrix is to being singular, and for a very simple reason. The determinant of the matrix is affected by scaling the matrix. Whereas the condition number, suppose I take a matrix A and multiply it by the scaling factor C. Then A inverse would be multiplied by C inverse, and the C and the C inverse would cancel out. So the condition number is scaling invariant. To take the condition number matrix from MATLAB, you can do cond of A. An optional second argument to use um, whatever p norm you like for purpose of computing the norm, p norm of A and p norm of A inverse. No matter what norm you use, the computing condition number is expensive. But default is to use the 2 norm. Because you have to deal with the computing the norm of the inverse somehow. Which, and like in the 2 norm, this would be the largest singular value, and then norm of A inverse would be 1 over the smallest singular value. So that could be expensive. But that's why it's actually an active research area to try to estimate the condition number of a matrix more efficiently than actually going in trouble computing the condition number to avoid that overhead. Okay. So questions about the condition number?
So condition number is basically the product of norms of
Yes.
a given matrix.
Yeah.
How any relationship applies to, like, is valid for all factors.
Yeah, so you can take a condition number in any norm.
You would get the same value.
Not the same value, but in the ballpark. Like, you will not have a situation where a matrix is well conditioned in one norm and ill conditioned in another. Kind of cool though. Okay. All right, I'm gonna take a little time to do a MATLAB demonstration involving the condition number. Okay. So I'm going to create a matrix 2 by 2. The entries might seem random, but they're not. So 2 by 2 matrix. I'm going to create 2 right-hand side vectors. Make sure I'm typing these in right. Okay. Another one. Okay. Now, these vectors don't seem very different from one another. So in fact, if I take the norm of the difference between them, the relative difference, let's see what we get. All right, so roughly 1% difference between them. Okay. So you might think, if I'm going to solve A is equals B, with B1 and B2, that solutions should be, you might think that, oh, maybe we're not much more than 1% different from one another. Let's find out. I'm going to compute x1 as a solution to ax equals b1, so first right-hand side. Okay, so here's my solution. All right. Now, I do the same with b2. A little different. I'll find out. The condition number of A, although I've seen much worse, even from your work. That's just come by. It's not a common condition number, like or like 10 to 10 or something like that. You really got it, yeah. So now we'll look at the norm of the relative difference in the solutions. So the right-hand side, these differ by 1%. So I do the same with the solutions. So there's a 300% difference between them. So now what I'm going to do is I'm going to take that relative difference. So this is the relative forward error, and I can divide it by the relative difference in the right-hand side vector. So you can think of that as the relative backward error. So a ratio of magnitude of forward error to backward error is how a condition number is defined, or it's the maximum possible ratio you can get. And yeah, those are pretty much in the ballpark. So, and I will admit, full disclosure, this example was contrived to, because what can happen is, really what the condition number tells you is, if you change the problem by a certain amount, the solution could potentially change by a certain amount. It's not necessarily going to, but it could. Now, if I look at the singular values of A, the small singular value indicates, in a sense, distance to a singular matrix. So not very distant at all. Let's do format long and do that again. Okay, so it's not, the small singular value is not 0, but it's pretty dang small. The condition number is the ratio of the largest singular value to the smallest. And sure enough, as you can tell from these numbers here, that would be this large number, certainly. So yeah. So that's the sort of thing that can happen at the matrix zero condition. You might not be able to trust the answer that you're getting. And then the thing is, if all it takes is a little bit of roundoff error to throw off your solution to that degree, then you might be thinking like, well, why bother? And that's actually why, for example, we don't bother numerically computing what's called the Jordan canonical form of a matrix, because at least a solution to AX equals B, even if it can be thrown off by this much, at least a solution of AX equals B is a continuous function of the elements of A and B, whereas the Jordan form is not even continuous. Like a little bit of rounding error to change a 0 to a 1. And that's too serious a trust issue to overcome. Okay. So now you have an example illustration of equals of ill-conditioned matrices. And I just remember that even though I have 26 minutes left in class, I still have something else to cover. But okay, there's very little left, so we're good. So so here's a so suppose you solve x equals b by whatever method, Gaussian elimination, and you get your approximate solution x hat. And of course, we want x hat to be as close as possible to the exact solution. That'll just be called just plain old x. Now, unfortunately, we don't know. I mean, we don't know the exact solution, so we can't really compute this error. Now, what we can do is compute what's called the residual. So basically, you're taking your computed solution, you're substituting it back into the original equation to see how well it satisfies. This ought to be 0, but it won't be exactly. What you really get is called the residual, R, which is b minus ax. Now, even though the residual is not the same as the error, there is a close relationship to that. So this is the actual error. What is the difference between my computed solution and the exact solution? So if I take the error and multiply it by a, so then I get a times z is a times x minus ax hat. But ax is the exact solution, so ax is equal to b. So I end up getting this b minus ax hat, but that's a residual. So in other words, a times the error equals the residual. So you might think, oh, well, if the residual is small, surely the error is small. Well, that's not entirely true. You have to take a condition number into account. So if I look at what is the relative error, I mean, I looked at the relative error before, but now from a slightly different perspective. Well, the error, now that we know that error is A inverse times the residual, and then I use the properties of norms, I can say this is less than or equal to norm of A inverse times norm of R. And then I multiply and divide again by the norm of A, then I get this, that the relative error in X is less than or equal to the relative residual, so norm of R divided by norm of B, but times the condition number. So what that means is it's possible that the residual might be very, very small and the error could still be large. Like, let's suppose your residual has a norm of 10 to the minus 15, but your condition number is 10 to the 10. So then your relative error solution might be in the order of 10 to the minus 5. So you have to be careful about that. But unfortunately, residual is something that we can compute, so it is often used as a measure of accuracy. I want to point out one thing that happened algebraically down here. B is equal to AX. So a norm of B is less than or equal to norm of A times norm of X. What that means is if I take a reciprocal of both sides of this inequality, that means that 1 over norm of A times norm of X is less than or equal to 1 over norm of B. So that was used here to combine B's into the norm of B, as long as we have a less than or equal to here. Okay. Then it works out nicely that we have relative forward error, and this is a notion of relative backward error, if you will. Okay. Now, residual can be used to try to improve the accuracy of our solution using this relationship that A times the error equals residual. And that leads to what I can do is if I solve this system, I'd like to get the error. Of course, I won't get this exactly. What I'll get is an error estimate. And I can add that to my computer solution to get an improved solution. And I'm going to show you the algorithm that's in the text, where it's called iterative refinement. Oh. Okay. So here's the algorithm for iterative refinement. So initially, my computer solution is 0. My residual is just B, which if X is 0, the residual would be equal to B. And then I keep iterating, because it's this iterative refinement. So I solve this system. So the first time around, I'm just trying to solve A equals B, because the right-hand side is B. Then, what I do is, whatever I get, that's my error estimate, I add it on to the solution I have so far. And then I will update my residual. So whatever I got from my error estimate, I need to subtract off A times that to update my residual. So I keep solving this system again and again, but with a smaller residual. Hopefully that's going to 0. Now, most of the time we're doing our computation in what's called double precision floating point arithmetic. What has been shown is, suppose you're performing your computations in single precision, so each number is 432 bits rather than 64. But if you compute for residual, just that part in double precision, but you do everything else in single precision, and then what this algorithm will do is it will actually give you the exact solution up to the limits of single precision. So in other words, if you're able to compute the residual using a higher precision than what you would normally use, then iterative refinement will give you pretty much the exact solution in the lower precision, whatever that may be. So this is useful if you have access to use variable precision, and a lot of computer architectures do make it possible. It is possible to work with both single and double precision in MATLAB. It's just the default is to do everything double. The question about iterative refinement. Here's one thing I want to point out about this line right here. because I'm showing you that the residual is defined to be, b minus a times x, but I don't have it written that way here. Here I have new residuals is expressed in terms of the previous residual. Now that's mathematically equivalent to just doing b minus ax. But why is it better to do it this way? So, so here's what it would be from the definition. So if I take b and write it as, if I take, I'll just fill that in here. Hopefully it doesn't fill to a second page. So let's start with the definition. Okay. Now, I can add and subtract RK. Now, RK, I can rewrite as B minus A X. Okay. That's going to cause the B's will cancel. And then I have A, subtracting off A times xk plus 1 minus xk. But if I go back to the algorithm, we have this relationship between xk and xk plus 1. Xk plus 1 minus xk equals tilde ek. And that shows up here. So the reason why is far better to use this formula instead of this one is residual is supposed to be going to 0. The error also is supposed to be going to 0. So we're subtracting both quantities that are getting smaller and smaller to get something that is hopefully smaller still. Whereas in this case, b is a fixed vector, fixed magnitude. And xk plus 1 is approaching the exact solution. So this is also approaching b. Here we're subtracting two vectors that are not going to 0. When you are subtracting two vectors, matrices, whatever, that are close to one another, but the difference between them is much smaller than their own magnitudes, that is catastrophic cancellation. So anytime you're computing x minus y, and if the result is much smaller than both x and y, that's cancellation. So this formula is safer because, yes, these are getting close to each other, but they're both getting close to 0. So they're smaller than what we have here. So we still might incur some cancellation error, but it's a lot less than what this would give. So, anytime you have something like that, if you're subtracting two items that are meant to be of a substantial magnitude, not going to 0, it's worthwhile to try to rearrange that to compute it in a more stable way. Okay. It's little things like that that end up making quite a big difference sometimes. Okay, so that brings chapter 3 to an end. Does anyone have any homework questions?
I have question 9.
Which one?
Question 9.
Oh, no, 3.2?
Yeah, 3.2.
Okay, let's go there. Okay,
So the function takes two inputs,
yeah.
L and B. So you give us, L.
Yeah, just create a random B.
Okay.
Yeah, and then you can do L/B to see what you're supposed to get.
I have a question.
Oh, yeah.
Number 11. I'm not sure what will be the output. So you say there's two conditions. One is if I is greater than j, then the entry is equal to the multiplier mij.
Yeah.
And else it will be uij. So the output will be a single matrix.
Yeah, one matrix where, because after doing Gauss elimination, you're getting the entries of U in the upper triangle anyway. So the only thing that you'd be doing differently than like the previous Gauss elimination, like reverse homework, is that you are storing the multipliers in the lower triangle. Because the Gauss elimination algorithm that you would have implemented here just leaves whatever in the lower triangle, it's meaningless. But now you're just going to put the multipliers in those positions. But yeah, there's only one matrix that gets returned that has both L, the interesting part of L, and U in it.
So I'm not sure if I understand that question. I mean,
Okay.
11. Can you say it again?
Okay, so what's happening is it's mostly going to be like this. I mean, you're not dealing with B, and that's gone. But the only thing you have to do differently is because this will cause, like the one condition that the problem states that for I less than or equal to j contains the elements of U. That's going to happen anyway. You don't have to do anything extra for that. But the way this algorithm works, you have these multipliers in Mij, and this isn't really storing them anywhere. Or if you translate this directly, literally to MATLAB, maybe it's storing it in some matrix M that is then not used. But what happens is, as you're going through Gauss elimination, for I greater than j, once you carry out that row operation, nothing really happens with those entries in the lower triangle. So that there's no meaning to them. So that is storage space that you can use. So when you are computing your multiplier, you can also handle storage of a multiplier. And the ij position is where it should go. And you're not using that ij position for anything else. So might as well go there.
Yeah, so when I try to solve this, this problem number 11, so I'm getting something in lower triangle, the mij value, but the upper triangle, I get only zeros.
Okay, that's very strange. Because, so whatever matrix you take as input, your A, you should just be doing everything with an A. There's actually no need to use any other matrix. So it's strange you would be getting zeros. Do you have your code handy?
Yes.
Okay. Okay, so oh, I see why it's happening. Because this loop, I goes from j plus 1 to n, I is always greater than j. So So this happens, that this statement will never be run. So you wanna make a storage unconditional, so really the best thing to do is, if you work entirely with A and store the multipliers in the lower triangle of A, and then when that's done, that's your LU. And you can just assign that to LU. Yeah, so you are doing the storage right. It's just that you might as well wait till the end to well actually what you're also allowed to do is, because right now your function's written as function LU equals Gauss lim of A, but you can have the input and output overlap. You can have A equals Gauss lim of A, and then you're overriding A. So then that way there's no need for an extra assignment statement at the end that just says like LU equals A,
Oh,
because that's wasteful copying. But yeah, when you have statements like that doing something with IJ, it's important to keep in mind what values of I are actually being assumed, because if you were iterating over the whole matrix, then that would have worked. But here I is limited. Okay. Still a few minutes. Any other questions? Homework?
So, question 14, do you want us to do it in MATLAB?
Oh, okay.
14 and 15.
Okay, that can be done either on paper or in MATLAB. You might find it easier to do it by hand, because otherwise you have to code up all the logic of the comparisons and so forth. Such a small matrix. I think most students do it by hand, but up to you.
Okay.
Let's go look at the result anyway. Anything further? Okay, I guess that's it.